This is Wonders of the Universe, and you're gonna want to get comfy for this one as we explore the gas giants. It's going to be quite a long one because I think we'll all agree these are the most spectacular planets in our solar system. The gas giants. What is the difference between a star and the planets that form around it? The solar system's largest planet shows that the line separating one from the other can blur. When the solar system first began to form, the heat radiating out of the new sun blew away the hydrogen molecules in the surrounding accretion disk, so that the regions closest to the sun became, by default, richer in the scarce, heavier chemical elements like iron and silicon, while the outer regions of the disk, where the sun's radiation was not so intense, were able to hold on to the more widely available hydrogen. This explains why the inner planets of the solar system are small, rocky and dense, while the outer worlds are mainly giant spheres of gas dominated by hydrogen. Jupiter, the greatest of the four gas giants, given more time and gaseous material to feed upon, this massive hydrogen-rich ball might have become a star in its own right, a brown dwarf. Too small to reach ignition point, but a kind of star nonetheless. Saturn's famous ring system consists mostly of water ice and grains of dust. The rings extend hundreds of thousands of kilometres from the planet, yet their vertical depth is negligible. Viewed edge-on, they almost vanish. Uranus, the third gas giant, is a dynamic world with some of the brightest clouds in the outer solar system, and its own faint ring system. The atmosphere is mainly hydrogen and helium, with a small amount of methane. Neptune, a similar world to Uranus, orbits the Sun once every 165 years. Unlike all the other planets, it is invisible to the naked eye because of its extreme distance from the Earth. Jupiter is the fastest spinning planet in the solar system. It takes less than 10 hours for a complete rotation around its axis. The rapid rotation of this massive planet causes its equator to bulge outwards. Rotational energy also shapes the atmosphere, the clouds, and the storm systems into distinct bands. The famous Great Red Spot at the lower centre of this image was first observed by astronomers more than 300 years ago, and it shows no signs of abating today. Jupiter's Great Red Spot and the banded features of the atmosphere can be seen in any reasonably decent optical telescope, but professional astronomers tend to augment the details through multispectral analysis. No one knows how long Jupiter's famous Great Red Spot storm system has raged, nor how long it will continue. It seems to behave like a hurricane on Earth, but is enormous. 3 Earths would fit within its boundaries. Located in Jupiter's southern hemisphere, its rotation is counterclockwise, and it takes about 6 days for one of those rotations. This succession of images shows the red spot moving through the upper atmosphere. This is how Jupiter looked on the 12th of December 2000. Small bright spots in the dark bands above the equatorial region are thunderstorms. We never see this view of Jupiter through our telescopes. but this image, made up from narrow angle images taken from the Cassini spacecraft, is what the familiar planet looks like if seen from above its north pole. Here we have a close-up image of the Great Red Spot, revealing the complexity of its structures and energies. Time-lapse images of other weather systems and atmospheric features on Jupiter. If the Great Red Spot did not exist, the rest of the planet's weather system would still impress us with their immense scale. This composite of the Jovian system's major objects includes the edge of Jupiter with its Great Red Spot and Jupiter's 4 largest moons, known as the Galilean satellites in honour of Galileo, the astronomer who first discovered them. From the top to the bottom, the moons shown are Io, Europa, Ganymede and Callisto. The moons are to scale, but are artificially grouped together for clarity. Saturn's rings are so obvious that they can easily be seen in any decent telescope. Jupiter's rings are more subtle, but backlighting from the Sun reveals them. The rings were only discovered in 1979, when the first space probe visited the planet. 2 simultaneous eruptions are visible on this image of Io, viewed from the Galileo space probe. On the right, a bluish plume rises above the surface of a volcanic caldera known as Pilon Patera. In the middle of the image, near the shadow line where night meets day, another plume is seen from directly overhead, casting a dark shadow on the left of the volcanic vent that ejected it. Sulphurous yellow compounds stain the surface of Io. Red areas seem to indicate fresh lava flow. Io is affected by immense tidal forces from Jupiter. As a consequence, the moon's crust is never stable, and its molten interior constantly breaks through onto the surface. Details of Io's surface show hot molten lava bursting through the obviously fragile crust. Here we have another extraordinary view of Io as it passes across the face of Jupiter, casting a deep black shadow on the top of the Jovian atmosphere. When Io interposes itself between the spacecraft and the Sun, the eclipse enables the probe to monitor delicate phenomena that would otherwise be swamped by solar radiation. These images show varying accumulations of volcanic gases in Io's thin atmosphere. Jupiter's innermost moon crosses the face of its incredibly huge parent planet in this haunting image from the Cassini space probe. NASA's Pluto-bound New Horizons spacecraft passed through the Jupiter system in early 2007, riding the planet's gravity to boost its speed and shave 3 years off its trip to Pluto. As it passed, it captured this spectacular view of Io in the foreground. Detailed views of the European surface reveal features that look almost exactly like pack ice on a terrestrial Arctic sea. The flows break up, then refreeze in new positions. An even closer look at cracks between the flows shows brownish material that seems to have oozed up between the cracks, then froze in place. This brown discoloration may come from the subsurface water. scientists think that this water may contain organic material. This impact crater, Powell, is named for a characteristic in Celtic mythology. Powell's visibly dark central region is about 26 kilometres, or 16 miles in diameter, while brilliant white rays of debris blasted from the impact site extend outwards for hundreds of kilometres. The white debris clearly overlays everything else on the European surface, indicating that this crater is younger than the surrounding features. Europa, Jupiter's fourth largest moon, has a frozen surface, but it is probably much warmer in its interior. A deep liquid ocean of water may lie under the surface ice. The relative scarcity of impact craters suggests that Europa swiftly smooths away its scars. An extreme detail of the cracks between the fragmentary chunks of ice shows the intricate pattern of melting and refreezing. Ganymede is Jupiter's largest moon, and the largest in the entire solar system. It is also the only moon with its own magnetic field. This suggests that it has a molten iron-rich core. A chain of craters on Ganymede, named Enki Katina, may have been created by a comet that was pulled into pieces by Jupiter's gravity as it passed too close to the planet. Soon after this breakup, the fragments crashed into Ganymede in rapid succession. Complex tecton crustal plates are evident in this image of Ganymede's surface, showing the border between a region of ancient dark terrain known as Marius Regio and another area of younger terrain named Nippur Sulcus. The curved appearance of this feature is probably due to simultaneous twisting and sliding of the plates. A computer model of Ganymede's surface shows its deep groove caused by tectonic distortions in the crust. Light branching bands from the most obvious impact crater on Ganymede suggest that a thick underlayer of ice has been exposed by the force of impact. A more distant view of Ganymede, which is about 1.5 times the size of our moon, but only half as dense. It is probably composed of a mixture of rock and ice. This picture of Callisto was taken by Voyager 2 from a distance of 2,318,000 kilometers, or 1,438,000 miles. Callisto is covered with bright spots, which are meteorite impact craters. The largest of them, a prominent bullseye-shaped feature, is similar to Mare Oriental on our moon, or the Caloris Basin on Mercury. Jupiter's second largest moon is about the same size as the planet Mercury. It orbits just beyond the reach of Jupiter's fierce radiation belt. Callisto is the most heavily cratered satellite in the solar system. Its crust is very ancient and dates back to just shortly after the solar system was formed. Saturn is the second largest planet in the solar system, with an equatorial diameter of 119,300 kilometers, or 74,130 miles. It is visibly flattened at the poles, a result of the very fast rotation of the planet on its axis. Its day is 10 hours 39 minutes long, and it takes 29.5 Earth years to orbit the Sun. The atmosphere is primarily composed of hydrogen with small amounts of helium and methane. The planet as a whole is less dense than water. In the unlikely event that a spectacular vast ocean became available, Saturn would float in it like a cork. The distinctive and beautiful rings are split into different zones. The most notable gap is the Cassini division, the wider of the two dark bands clearly visible here. The bright swirl at the top right of this image is an electrical storm raging in Saturn's atmosphere. Essentially, this is a display of lightning bolts so large that it could encompass all of the continental United States. Such storms are thousands of times more powerful than any equivalent outburst on Earth. Solar wind from the Sun interacts with all planetary atmospheres in the solar system. On Earth, we see characteristic aurora, displays of glowing light, in the skies near the North Pole and South Pole. This sequential image, scanned in ultraviolet, shows a Saturnian equivalent. And this sequence of 5 images, captured at regular intervals by the Hubble Space Telescope between 1996 and 2000, show how our view of Saturn's ring system changes over time. The Cassini spacecraft drifted in Saturn's shadow for about 12 hours and looked back towards the eclipsed Sun. The night side of Saturn is partly lit by light reflected from its ring system. Visible in spectacular detail is the outermost ring, created by the newly discovered ice fountains of the moon Enceladus. The rings of Saturn seen edge-on vanish to the thinnest line, while casting vast shadows across the top of the planet's atmosphere. Moons appear as tiny bumps in the ring line. Seen from high above Saturn's North Pole, the planet's bulk casts a colossal shadow over its rings. An edge-on view obtained by Cassini in March 2006 shows the thin silver of the rings silhouetted against Saturn, with Rhea hanging below the unlit rings. As the beautiful backlit conditions change from Cassini's point of view, and the glare fades, Earth becomes visible as a distant and tiny dot of light in the background. Most images returned by space probes and orbiting telescopes are colour enhanced to pick out subtle details. This is how Saturn looks when seen through a conventional telescope and through human eyes. It is still intensely beautiful, but special instruments are required to see its underlying atmospheric dramas. The tiny moon Prometheus passes upwards through Saturn's F ring and eventually pulls clear. What looks like a shadow behind Prometheus is in fact the path of clear space that is gravity and temporarily gouged through the ring. The influences of moons may be at least part of the cause of spokes and other patterns within the rings. The mechanisms that drive these complex and shifting formations are not yet understood. Scientists once thought that Saturn's rings were almost completely flat and extremely regular in construction, but new images reveal occasional strange bumps, some as high as the Rocky Mountains. This composite image was made from 65 individual observations by Cassini's visual and infrared mapping spectrometer in the near-infrared portion of the light spectrum. This extraordinary Cassini image shows the shadow cast by Mimas across Saturn's rings. Saturn's moons orbit close to the ringed plane, but not quite in line with it, so that from certain angles they cast elongated shadows across the rings. Low-angle illumination from the Sun causes the moon Mimas to cast an extremely elongated shadow across Saturn's rings. The shadows were seen as the Sun crossed Saturn's equator during August 2009, bringing the spring season to the planet's northern hemisphere for the first time in almost 30 years. Conjunctions of Saturn's rings and its moons, and the slanting of sunlight, provide endlessly variable and fascinating panoramas. Enceladus traverses from the dark to the light zones in this view from above Saturn's southern hemisphere, and Mimas is backdropped by the rings in this view from the south. Twice in every Saturnian orbit, the rings are visible edge-on from the point of view of Earth's telescopes. 4 moons can be seen from lower left to upper right: Enceladus, Mimas, Dione, and Titan. The Cassini space probe used infrared cameras to penetrate Titan's thick atmosphere and reveal the moon's surface. The following 2 images capture Titan's opposing hemispheres. Well, this image is the same as the first, 2.5 months later. Variations in colour are caused by weather and the changing distribution of the various ices on the surface. Titan is the only moon in the solar system to possess a substantial atmosphere. An image taken by Cassini shows its haziness and rich colour, while this edge-on view shows its impressive thickness. Sequential views of the approaching surface of Titan, viewed by the Huygens probe in January 2005. The surreal distortions are created by the very wide-angle lens that was used to capture as wide a panorama as possible. Radar mapping of an area of Titan known as Sotra Facula provides good evidence for an ice volcano, or cryovolcano. Multiple craters are as deep as 1,500 meters, 5,000 feet. The image also shows finger-like flows of ejected material. In this colour scheme, blue suggests the presence of exposed ice. Infrared light from Titan shows a large cloud formation in the moon's south polar region. The clouds accumulate and drift much like clouds on Earth, but in a slower, more lingering fashion. This is a consequence of the extremely cold conditions. This simulated view, generated by data from the Huygens probe, shows what Titan's surface would look like through human eyes, and without the space probe's wide-angle distortion. The liquid lake in the foreground seems as clear water, but is in fact methane. Cassini carried a small landing probe called Huygens, designed to reach Titan's surface. This distorted fisheye view is what Huygens saw as it fell through Titan's atmosphere and approached the surface. Rough, bright, icy terrain surrounds dark, flat lakes of liquid methane. Erosion features and channels carved by liquid are evident in this view of Titan from the descending Huygens probe. Subsequent radar mapping shows flat lakes of liquid methane. Tethys is larger than either Mimas or Enceladus. Its surface is relatively bright, but heavily cratered. Obviously, the crust does not rapidly reshape itself like the icy surface of Enceladus. Ithaca Chasma is a long trench or valley extending around much of the Moon's surface, possibly created when layers have collapsed under their own weight. Alternatively, it may have formed from rock, as the crust cooled soon after its formation, so that all we see is the approximate ice-encrusted outline of a much deeper floor. This Cassini image shows Dione, Tethys, and tiny Pandora from just above the plane of Saturn's rings. The apparent closeness of the moons is deceptive, a product of Cassini's powerful telescopic system. Dione and Pandora are in front of the rings, while Tethys is behind them. A closer view of Dione shows a network of bright streaks on the left limb. These are cliffs of ice. Plumes of ice material ejected from fissures in the crust of Enceladus can reach at least 1,000 kilometers, 600 miles, into space. The ice geysers arise from near-surface pockets of liquid water with temperatures substantially higher than the Moon's deep frozen surface. An ice plume ejected from Enceladus sends particles streaming into space hundreds of kilometers above the south pole of this highly active moon. Some of the particles escape to form the diffuse outermost ring around Saturn. This colour-coded image was processed to enhance faint signals, making the fainter, larger scale components of the plume easier to see. Because of its bright icy exterior, Enceladus has one of the highest levels of reflectivity of any object in the solar system. The grooves and the ridges in the southern hemisphere seem to be where the crust comes under the greatest stress, probably as a result of Saturn's tidal pull. Iapetus is unusual in that large areas of its surface are markedly dark and others are very light. This moon turns on its axis once every 80 days. The slow turning has complex consequences, and it seems that dust from the rings and from other moons deposits onto one hemisphere of Iapetus, but not the other. Here we have a mosaic of two high-resolution images taken during Cassini's New Year's Eve 2004 flyby of Iapetus. The North Pole is approximately 15 degrees below horizontal on the right. The dark deposits become patchy and diffuse as the surface transitions into much brighter and icier terrain near the pole. The tremendous collapse of material on Iapetus created this distinct ridge, known as Cassini Regio. The fact that it extends so far across the surface suggests that the material may be very finely grained. The material appears to have collapsed from a scar 15 kilometers, 9 miles high. Iapetus is more intriguing because it has a large and unusual bright patch on its surface, and a strange seam-like ridge along its equator, almost as though the moon's crust is in two halves, joined like the halves of a walnut shell. High-resolution scans of the transition region between the bright and dark hemispheres on Iapetus reveal the bright water ice spotted with darker carbon-rich material. The images were taken in September 2007 as the Cassini spacecraft approached to within 5,260 kilometers. That's 3,270 miles. Another close-up view taken on that same flyby shows mountainous terrain reaching about 10 kilometers or 6 miles high along the unique equatorial ridge of Iapetus. Saturn's moon, Rhea, is little more than a ball of ice with a small rocky core. The obvious impact scar on Mimas, some 140 kilometers or 87 miles wide, is called Herschel crater. Mimas may be small, but its gravitational influence is largely responsible for keeping the Cassini division of Saturn's rings relatively clear. Rhea and the smaller moon Epimetheus are seen partially obscured by Saturn's rings. Here, in a later orbital space probe pass, Rhea is backdropped more clearly against the rings. Rhea has an extremely thin oxygen atmosphere, almost but not quite undetectable. In March 2010, the Cassini probe scooped a tiny sample of oxygen and carbon dioxide while passing overhead at an altitude of 97 kilometers or 60 miles. The wispy atmosphere is sustained by high-energy particles slamming into Rhea's surface and kicking up atoms and molecules. Mimas' largest impact crater spans a third of the moon's diameter. If the object responsible for this had been any larger, it would have shattered Mimas into fragments, probably creating another of Saturn's rings. The walls of Herschel crater are approximately 5 kilometers or 3 miles high, but parts of the floor descend 10 kilometers or 6 miles below the rim. One of Saturn's moons slips behind another in this time-lapsed pair of images taken during 2004. Titan's dense and hazy atmosphere is obvious as Cassini sweeps through the Saturnian system. Its perspective shifts and it sees small, battered Epimetheus and smog enshrouding Titan, with Saturn's A and F rings in the foreground. The Cassini spacecraft observes a pair of Saturn's moons with the hazy sphere of comparatively giant Titan behind the smaller Saturnian moon, Tethys. Hyperion is strewn with strange craters and has a very peculiar sponge-like surface. The bottom of most craters contains some type of unknown dark material. Hyperion is small at about 250 kilometers or 155 miles across. It rotates chaotically and has the density so low that it may hide a vast system of caverns inside. Pandora is a fragment from a larger object that was pulled apart by Saturn's gravity. Epimetheus is a so-called shepherd moon. Its gravity, though very weak, helps to define the shape of Saturn's faint outer F-ring. Callisto is known as Tethys Trojan because, together with Calypso, it circles Saturn in a similar orbit as the moon Tethys. Callisto is about 24 kilometers or 15 miles across and appears to have a smooth, icy surface. It doesn't show the signs of intense cratering seen on many of Saturn's other moons. As its appearance suggests, Phoebe is probably a stray asteroid caught by Saturn's gravitational field, but traces of carbon dioxide ice have been identified on its surface. This is not a characteristic of other asteroids. At first glance, one of the blander-looking planets, Uranus, has some of the brightest clouds in the solar system, and its own faint ring system. The atmosphere is mainly hydrogen and helium, with a small amount of methane and traces of water and ammonia. The blue-green colour results from methane absorbing the red portion of the sunlight that strikes the planet, while the blue-green portion is reflected back into space by the cloud tops. Uranus may have been struck by a planet-sized object early in its life and knocked onto its side. Consequently, its axis is tilted to such an extent its north-south axis almost points towards the Sun. This image shows the similarly tilted faint ring system. NASA's robot spacecraft Voyager 2 passed by Uranus and its moons in 1986. Miranda, the innermost of the large moons, is heavily cratered and grooved. Its surface may be mostly water ice, but this relatively low-density world probably also contains silicate rock and simple organic compounds. 13 bands have been identified in Uranus's faint ring system, which is much less reflective than Saturn's. The rings probably consist of water ice fragments. The additional presence of carbon-rich dust may explain why the ices appear so dark. This colour composite of the smallest of Uranus's 5 major satellites was taken by Voyager 2 in January 1986 from a distance of 147,000 or 91,000 miles. Miranda's rough terrain has many fault valleys, ridges and impact craters. Infrared images acquired at intervals by the Hubble Space Telescope show movements of clouds on Uranus and variations in their distribution. Notice the especially bright cloud in the middle of the image. Here we have a montage of Uranus's 5 largest satellites in order of increasing distance from Uranus. They are Miranda, Ariel, Umbriel, Titania, and Oberon. The largest, Oberon and Titania, are about half the size of Earth's moon, or roughly 1,600 kilometers or 1,000 miles in diameter. Data is incomplete for Miranda and Ariel, and the grey circles depict the missing areas. To a similar world to Uranus, orbits the Sun once every 165 years. Unlike all other planets in the solar system, it is invisible to the naked eye because of its extreme distance from the Earth. It was first seen in a telescope in 1846. Astronomers at the time knew it must exist, or else the equations describing the orbits of the other planets would have been wrong. Neptune's orbit marks the boundary where the solar system's principal realm of major planets and moons ends, and a vast outer region sparsely occupied by dwarf planets and cometary wanderers begins. Clouds on Neptune move at different speeds depending on their altitude. The great dark spot at the centre of this image circles the planet more slowly than the small dark spot at the bottom. Almost everything we know about Neptune is derived from the Voyager 2 flyby in 1989. More recent Hubble telescope observations suggest that the great and small dark spots were transient. Seen from afar and scanned in conventional optical wavelengths, Neptune looks like a vast, uneventful sphere. Closer investigations shows features such as the Great Dark Spot, here seen 45 hours before Voyager 2's closest approach at a distance of 2.8 million kilometers, or 1.7 million miles. Feathery white clouds overlie the boundaries of the dark and light blue regions. The spiral structure of both the dark boundary and the white clouds suggests a storm system rotating counterclockwise. High-altitude clouds often stretch into long streamers shaped by strong winds and the Coriolis forces of Neptune's rotation. The streamers cast shadows on the blue layers of the atmosphere beneath them. At first glance, the dark streaks and fuzzy spots in this view of Triton, Neptune's largest moon, look like surface coloration. They are actually the shadows cast by plumes of nitrogen gas and dust ascending into Triton's thin atmosphere. Following of both Neptune and Uranus is affected by trace quantities of atmospheric methane gas. The Voyager 2 space probe identified high-altitude methane on Uranus. Is as small as 100 kilometers or 62 miles across can be seen in this colour image of Triton, photographed by Voyager 2 in August 1989. While it was still 5.4 million kilometers from Neptune. Triton's pinkish colour may be due to chemical products created by solar radiation working on methane gas and ice. As Voyager approaches the bright southern hemisphere of Triton, which fills most of this frame, is clearly reddish pink in tone. The surface of Triton is very rugged, scarred by chunks of ice, cluster faults, volcanic pits and lava flows composed of water and other ices. The surface is also extremely young and sparsely cratered, and is still geologically active today. This scene is 500 kilometers or 310 miles across. In this composite of Voyager 2 images taken through violet green and ultraviolet filters, a layer of pinkish material stretches across the centre of the image. The elongated dark streaks may represent dusty materials blown in the same direction by prevailing winds, and the white material may be frost deposits. Triton's extremely tenuous nitrogen atmosphere extends 800 kilometres or 500 miles above the surface. And that, my friends, concludes our look at the gas giants. If you gathered any information or enjoyed this at all, do please hit the like button and subscribe to the channel, and hit the notification bell, and you'll be alerted when our next episode on Ice Wanderers is uploaded. Thank you very much for watching. Take care, everybody. Peace.